Hi guys, I will be talking about Newton's laws of motion. Newton has given three laws of motion. The first law of motion. A body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest and of uniform motion in a straight line imply zero acceleration. So the first law can be simply expressed as if the net external force on the body is zero, its acceleration is zero. Now, two kinds of situations are encountered in the application of first law of motion. In first case, we know that the net external force on the body is zero. So from first law, we can conclude that the acceleration of the body is zero. Example, a box of mass m on which four forces are acting. In x direction, forces F1 I cap and F1 minus I cap are acting. In y direction, forces F2 j cap and F2 minus j cap are acting. So the net external force on the body is F1 I cap plus F1 minus I cap plus F2 j cap plus F2 minus j cap, which gives F net equal to 0 I cap plus 0 j cap. Since the net external force on the body is zero, so from first law we can conclude that the acceleration of the body or the acceleration of the box is zero. In the second case, we know that the object is unaccelerated. That is, the acceleration of the body or box is zero. So we can infer from first law that the net external force on the object is zero. Example, a box kept on the ground. The two forces acting on the box are force due to gravity, which is acting downwards, and the normal force R on the box by the earth in upward direction. The box is at rest, so from the first law, the net external force on the box is zero. So we can find the value of R using first law, which comes out to be R equal to W. Let us discuss about second law of motion. The second law of motion refers to a general case when there is a net external force acting on the body. It relates the net external force to the acceleration of the body. Now let us define momentum. Momentum of a body is defined to be as the product of mass of the body and velocity of the body v, and is denoted by letter p. Momentum is a vector quantity and its direction is in the direction of velocity v. So p equal to mv. Example, a box of mass m moving with velocity v. The momentum of the box is p equal to m into v, and the direction of momentum is in the direction of velocity. Let us discuss the importance of following quantities for considering the effect of force on motion. First one is mass. Example of a truck and a car can be taken. We know that truck is a heavy vehicle and its mass is denoted by capital M, and car is a light vehicle and its mass is denoted by small m, where capital M is greater than small m. So the observations are: a much greater force is needed to push the truck than the car to bring them to the same speed in same time, and a greater opposing force is needed to stop a heavy body, that is truck, than a light body, that is car, in the same time if they are moving with same speed. So the mass of a body is an important parameter that determines the effect of force on its motion. Another important parameter is speed. Let us take an example of a bullet of mass m. In case 1, bullet is moving with very high speed v1. We know that in this case, it can easily pierce the human tissue before it stops, which results in casualty. While in the second case, the bullet is moving with very low speed v2, and we know that it will not cause much damage. So our observation is, for a given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. So taken together, the product of mass and velocity, that is momentum, is evidently a relevant variable of motion. The greater is the change in momentum in a given time, the greater is the force that needs to be applied. Another important parameter is time. An expert cricketer catches a cricket ball coming with high speed far more easily than a new player who can hurt his hands in the act. One reason is that an expert player allows a longer time for his hands to stop the ball by drawing his hands backward in the act of catching, while a new player, on the other hand, keeps his hands fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly, and this hurts. So the conclusion is clear. Force not only depends on the change of momentum, but also on how fast the change has been brought about. The same change in momentum brought in shorter time needs a greater applied force. This gives us the basis of second law of motion. The statement of second law of motion is the rate change of momentum of a body is directly proportional to the applied force and takes place in the direction in which force is applied. Now for deriving the equation for the second law of motion, a body of mass m is considered. Initially, the mass m was moving with velocity v in this direction. Now after application of force F for a time delta t, the final velocity of the mass is v plus delta v. So a body of mass m where m is constant moving with initial velocity v has final velocity v plus delta v under action of force for a time interval delta t. So the initial momentum of the mass is m into v and the final momentum of the mass is pf equal to mv plus m delta v. So change in momentum denoted by delta p is m into delta v. According to the second law of motion, force is directly proportional to the rate change of momentum. So F equal to k delta p by delta t, where k is a constant of proportionality. Taking the limit delta t tends to 0, the term delta p by delta t becomes the derivative or differential coefficient of p with respect to t, denoted by dp by dt. So F equal to k dp by dt is the new equation. For a body of fixed mass, the rate change in momentum is equal to d by dt of mv, where since m is constant, so dp by dt equal to m dv by dt. So dp by dt equal to m into a. So the second law can also be written as F equal to kma, which is denoted by equation 1, which shows that the force is proportional to the product of mass and the acceleration a. Now since the unit force will be defined by equation 1, any constant value of k can be chosen. So the value k equal to 1 was chosen. So the second law is F equal to dp by dt equal to ma. Some important points for second law. Second law is a vector law. It is equivalent to three equations, one for each component of vector. Let F equal to fx I cap plus fy j cap plus fz k cap and P equal to px I cap plus py j cap plus pz k cap and A equal to ax I cap plus ay j cap plus az k cap. So from second law, F equal to dp by dt equal to ma. So fx I cap plus fy j cap plus fz k cap equal to dpx by dt I cap plus dpy by dt j cap plus dpz by dt k cap equal to max I cap plus may j cap plus maz k cap. So fx equal to dpx by dt equal to max, fy equal to dpy by dt may, and fz equal to dpz by dt maz. So these three constitute three different equations. The second law of motion given by equation F equal to ma is applicable to a single point particle. F is the net external force on the particle and a is the acceleration of the particle as seen from an inertial frame of reference. However, the law is in the same form applies for a rigid body as well as to a system of particles where F is the total net external force on the system and a is the acceleration of the center of mass of the system. In the second law of motion, if F equal to 0, it gives A equal to 0, which is consistent with the first law. The second law of motion is a local relation, which means that force at a point in space at a certain instant of time is related to A at that point at that instant. Third law of motion. According to Newtonian mechanics, the external force on a body always arises due to some other body. For two bodies A and B, B gives rise to an external force on A. In turn, A also gives rise to an external force on B. The mutual forces between two bodies are always equal and opposite. Now the statement of Newton's third law of motion is to every action there is an equal and opposite reaction.